longer an abelian category. So the property of K being abelian depends on the category that you started with, on R in this case. It depends on the ring. So that's why it's, well, there might be something in trying to prove that K is not abelian. Let's do some of the checks that K is a category and it's an additive category. Now we have time. So, well, we need to check that we have an identity for every object, and the identity is going to be the class of the identity morphism in C. Composition is the one that we need to check. And to check that composition is well defined. So I want to check that if I have two morphisms, F is a morphism from C to D in the category of chain complexes, and G is a morphism in the category of chain complexes from D to E, then I have the class of F, which is a morphism from C to D in the category K, and then I have the class of G, which is a morphism from D to E in the category K, and I need to have this composition G composed with F. This is a morphism in the category of chain complexes from C to E, and I have this class. And I want to claim that, well, this should be equal to the class of G F. And this is the definition on this side. So I need to define you how composition works for morphisms, and I need to check that this is associative, that this is well defined, that the identity behaves as the identity, and so forth. So the fact that this is associative is on the note. Suppose that it's well defined, which is the hard part. The fact that this has to be associative is going to come from associativity on the category C. So if I have three morphisms now, G, H, and F, so now I have, suppose, an H, let's put it here, a morphism in the category of chains from E to F, then H composed with G composed with F, this is equal to H composed with G composed with F, and this happens in chains because chains is a category, and I take classes on both sides, and this by definition is the class of H composed with the class of G composed with F. That's just this definition. And this by definition is the class of H composed with G composed with the class of F. So I have this equal. And now again, by definition, this guy is the class of G composed with F with the class of F. And this is, by definition, the class of H composed with the class of G. And this guy is now being composed with F. So that's associativity on K. So associativity works on the nose. The fact that the identity behaves as an identity is absolutely trivial. If you put G or F here being the identity, then I'm going to have, let's say F is the identity. This is going to be the class of G. And this is going to be the class of G composed with the identity. So we're defining it to be an identity. Same if G is the identity, then the identity is an identity on both sides. So we have identities and we have associativity of the composition, but we need to check is that we have a composition. So I need to check that this guy here is well defined. That if I change G by another representative, then this class is the same. So essentially I need to check that if I have another, say G prime, that is homotopic to G, then I want to check that the class of G prime composed with F is equal to the class of G composed with F. Or in other words, I need to check that the composition of G prime with F is homotopic to the composition of G with F. And I need to find an explicit homotopy between those two. Okay, so for that, so what I am given is this homotopy between G prime and G. So I am given dn minus 1, dn plus 1. And here I have some en plus 1, 2en to en minus 1. And I'm given these maps, S and S, such that S composed with D plus S composed with D here, I get here G minus G prime. Or perhaps G prime minus G, depends. I think I defined it this way so that there is G prime minus G. Okay, so what I have is these maps S such that SD plus DS is equal to G prime minus G. So that's what I have. And what I want is the composition of that with F. That I am really stupid. I should have started that diagram here. So let's do this here quickly. So here I have this map F. And I can compose that map F with either G or with G prime. There are maps here. And I have these two maps, F composed with G and F composed with G prime. And I want to take the difference of these two, and I want to construct some map here from some map, well, let's do it here, like this. And it's clear that there's only one map that we can guess what the map has to be. We only have one map, which is from Dn to En plus 1. I'm going to compose that map with F. So I'm going to define S prime, probably perhaps S bar, to be F first and then S. That's the only map that we can guess that goes from Cn to En minus 1, to En plus 1. And, well, S bar D plus D S bar. This is, by definition, this is the composition of doing D, then F, then S. Plus D, then S, then F. And F is a map of complexes. So FD is the same thing as DF. Well, actually, I've chosen not a square. So FD is the same thing as DF. So here, I can put this F on the other side. And this becomes SDF plus DSF. And now this is SD plus DSF. And this thing here was G minus G prime or G prime minus G. So this is G prime F minus GF, which I wanted to check that were homotopic. So you do this on the other side, and you're going to check the composition on the other side is well defined. Or you can do both at once by composing with H. And then for arbitrary F and H, these two compositions are homotopic. OK, so that shows that composition is well defined, and therefore K is a category. Now, the fact that K is an abelian category, well, no, I'm sorry. The fact that K is an additive category, well, we do check that we have an object, 0 in K, that is going to be the class of the object 0 in chain, the complex 0 with the 0 differential. So that's a well-defined object. And, well, I claim that the addition is well-defined, with morphisms is well-defined. So the class of C plus the class of G, I define it to be the class of the sum in chains. And it's immediate to check that this is well defined. Right? The objects are the same in the category, so there's nothing to check. And if I have two morphisms, say f and f prime,
But we didn't take quotient on the objects.
that's what. We didn't take any quotients on the objects.
Why are we defining it?
Yeah, also find quotients in the bracket.
Oh, what do you mean by class? Yeah, so I'm just saying, I'm using class to mean the object in one category to differentiate it from the object in the other category. But yeah. So like if I write this, it looks like a bit weird. So I'm defining the direct sum. K has to have a direct sum, and I claim that on objects is the same, and I claim that on morphisms is also the same. So morphisms in the category chains from C to D. Yeah, so let me keep this class, and here class means the same object viewed in the category K. So this means C as an object in K. So if I have morphisms C and D between in the category of chains, then I declare the class of F plus the class of F prime to be the class of the sum in chain complexes. And I need to check that this doesn't depend on the choices made. I'll leave you to do because the chain, if I choose a homotopy between F prime and say F double prime, then the same homotopy is going to work for the sum. All right, so we have an additive category. And I made a bold claim the other day that this is not abelian. And it's not abelian depending on what category of chains I'm taking. Okay, so if every object in chains is split exact, for example, the category of, is split, like the category of vector, the complex of vector spaces, then the homotopy category is abelian. But otherwise it's not. And this is something that I want to hint instead of proving because it requires some work. So the theorem is, let me write a concrete theorem, and then I'll write a concrete theorem, I'll distill it, and then I'll only prove a little part. So every abelian triangulated category is semi-simple. So this is just a lot of words that don't mean anything. Let's try to make them mean something. So that theorem there is a corollary of this one, which is every monomorphism in a triangulated category is split. So that one is something that we can try to prove. And that would imply that one. So I'm not going to need this for a long time, so I'm not going to write it. But there's this word triangulated that we are going to define eventually, but not today. The thing is that K is going to be an example of such categories. And the statement is that, and there's this other word which is semi-simple. And the word semi-simple here means that every object is a sum of simple objects, in some sense. So this is going to prove that. And I'm not telling you what triangulated means, but K is such a category. So what I want to prove is that, and I haven't told you, there's another word here which is split. So let me tell you what that means. So let's say that we have a monomorphism. Then we have the kernel. Which is nothing. And then we have the co-kernel. If we had an abelian category, for example, some C. Let's suppose that we are in an abelian category. Let's forget about this for a second. So suppose we have some abelian category. This would be our situation. Okay? So if I have any morphism, then I look at the quotient that I have on abelian categories, and then this is a surjection, and I continue my morphism into a short exact sequence. This I can always do in an abelian category. Okay? So now, what I may not be able to do in an abelian category is find a map here making this composition the identity. Or in other words, finding another object here such that this B becomes the direct sum of these two. Right? In an abelian category, if I manage to find something like this, or if I manage to find something like this, making this the identity, then I express this B as a direct sum of A plus C. That's something that happens in an abelian category. Okay. Why is that? So suppose that I have, well, let's put names now. This is my injection, and this is my splitting, S. Then I look at the image of S, and since this guy is the identity of C, that image of S is isomorphic to C. Okay? So this B has inside A, it has inside the image of S, and this is isomorphic to C. So what I want to prove is that this S exists in K, and this S exists. So this S always exists in the category of K.
So are we taking those ABC in a particular category?
No, so this happens for an abelian categories whenever I can choose this S.
But in an abelian category, do we have images? Like SOs?
Yes, in an abelian category you do have images, and you do have co-images. So you define them to be the kernel of the co-kernel or the co-kernel of the kernel. So that's that's right. But what we do not have in an abelian category is this S. This might not exist in an abelian category. Okay?
But
So
if it exists, we have the sum.
if this exists for any short exact sequence, for example, on vector spaces, this exists for any short exact sequence, and that's why any vector space is always the sum. This B is always the sum of these two sides on vector spaces. But that's not true for modules over the ring of polynomials, for example. It's not, there are short exact sequences that are not split for arbitrary rings. Okay. But I want to prove that this guy actually, it does exist for K. Okay? So what are we going to do? So let's suppose that you have something like this, some morphism F like this, and we always have the cone of that morphism. If we have a morphism of complexes, we can always form the cone of that morphism. And remember, so this is an exact sequence. But we also have an exact, what was interesting about this cone is that we actually managed to do something like this. That was a beautiful thing about the cone, that it gave me a map. So it had a map from B into that guy, but it also gave me a map from the cone into this guy shifted by -1. And this also is exact. So that makes the splitting that we want. So I claim that having this makes, gives the splitting from the cone into B. Well, so it gives me this splitting that I want. Now for K, this is absolutely trivial. We constructed it. It's explicitly there. But the tricky part in this thing here is that, well, so a triangulated category is a type of category where this cone makes sense for an arbitrary morphism. You can no longer talk about exact sequences. It doesn't make any sense to talk about an exact sequence in K. This makes sense in chains, but not in K because I cannot talk about kernels and co-kernels in K. I am proving that they can't exist. So in K, what I can say is that I have a triangle. And that's why triangulated. I have a map from A to B to some other object, and then I can start shifting those objects to have from B to the cone, and then A shifted, and I can shift it again to get a map from the cone to A shifted to B shifted, and so forth. So we're going to get there later. But at least here, it should be clear that K, this is proving that K cannot be abelian, because if K was, then this morphism would be well defined on the category K, and then every object will be the sum of these other two. And that cannot happen. That just simply cannot happen, because if I am on an abelian category that is not every object is split, then I may have non-trivial exact sequences. Okay. All right, so that was it for this homotopy business. And we constructed the homotopy category. And I should start now with delta functors. But before doing that, because that's probably something that you've already done in algebraic geometry, I want to move on to some digression on graded algebras and give some examples of cohomology theories or homology theories. So I want to have in mind a non-commutative version. You might have done homology of sheaves already, so I want to do something different. I want to do homology of Lie algebras, to have something that looks different. I might do perhaps the RAM homology on manifolds, but I want to start with one notion, which is G is going to be a Lie algebra. So this is just to have something concrete in mind, and then I'm going to move to an abstraction in a second. So what is this? This is a K vector space. That has two operations. Well, I'm sorry, that has one operation satisfying two axioms. It has one operation, which is bilinear. Let's call the Lie bracket. That satisfies two axioms, skew symmetry, so skew symmetry says that AB is minus BA. If the characteristic of the field is 2, you may want to replace this by A bracket with A is equal to 0. If this is implied from this axiom, which is stronger, just take A to be A plus B and you're going to get this. But the converse is not true if the characteristic of the field is 2, so this is probably a better definition of skew symmetry than this. And the Jacobi identity which says that, well, A bracket B bracket C is equal to AB bracket C plus B AC. So this says that this is equivalent to saying that this operation, and this operation is an element, this is an element where? This is an endomorphism of G. Right? It takes B to the bracket of A with B. And not only this is an endomorphism, but this is a derivation of the unique bilinear operation in G. So this is the Leibniz rule for that endomorphism. This guy applied to this element B times C is this guy applied to B times C plus B times that derivation applied to C. So this is the Leibniz rule for that multiplication. I'm sorry, for this multiplication. So that's the Jacobi identity. And again, if the characteristic of the field is 3, you might want to add an extra condition. So if you took, well, let's not get there. For Lie algebras, it's not necessary, but if you're looking at super Lie algebras where this you're not allowed to do, so for those of you who know about super stuff, on a super Lie algebra, skew symmetry has a different form. So you're not allowed to require this. If A is odd, it might be that A bracket with A is non-zero. And then on a super Lie algebra, then if your field is of characteristics, so you cannot impose that. And then if you don't impose that, if your field is of characteristics 3, then you may have a Jacobi question about what happens when you put A bracket A bracket A, when A is odd. And then A bracket A bracket A, and A bracket A bracket A. If the characteristic is 3, then the sum of these 3 same elements is going to be 0. So we're more or less in the same situation. And then, well, you declare it that each one of these guys is actually 0. So that's a condition. But that's just a subtlety of super Lie algebra of characteristics 3. All right, but that's the notion of what a Lie algebra is. And I'm going to construct 2 complexes. This complex is going to be the complex that takes which dot, well, let's define it like this, which k of G. And this is well defined when k is bigger or equal than 1. And I'm going to write down explicitly the differentials. So this has this is wedge 1 of k. There's wedge 2 of k. There's wedge 3 of k of G, sorry, and so forth. So I want to give you what this differential is. Okay? So I'm going to write down here an explicit differential. And I'm going to put this guy here in degree 0. So perhaps, yeah, so probably. Now, let me extend this to the whole thing. Let me do that like this. Let's put k bigger or equal than 0. And then let's put this map to be 0. So this is wedge 0 of G. It's just the underlying field. And this map is just 0. OK, so I want to construct here this differential everywhere. Okay. And what I'll do is this is, well, a typical element in wedge K, a typical element in CK, is of the form A1, wedge A2, wedge AK, where these AIs are in G. And the typical element here is a linear combination of elements like this. This map Ds are going to be linear, so I'm just going to define it in elements like this. But you have to keep in mind that an element here is it's a sum of elements of this form. And I want to have a map from here to CK minus 1. Okay. I think I can probably write it here. So D of that guy is going to be a sum well, I'm going to get the signs wrong surely, but it doesn't matter. Minus 1 to the I. We're going to fix it immediately. So I'm going to actually, this is going to be only one summand because I've chosen trivial coefficients. So this is going to be 1 less or equal than I, less than J, less or equal than K. So I'm going to sum over 2 different elements, I and J. And what I'll do is this. I'm just going to put a sign. And now I don't care about this sign. Because I'm sure it's right. It doesn't matter if I add a plus or a minus 1. And then I'm going to take the bracket of AI with AJ. And I'm going to take the wedge product with A1, AK. But here, at some point, AI is not there, and AJ is not there. Okay, so I'm taking, out of these k elements, I've taken 2 of them, and I put this one element here, which is the bracket of those 2. So this wedge product has k minus 1 elements. I claim that this differential squares to 0. And of course, I'm not going to prove that. I'm not going to write that in the proof of that. I'm only going to check that. Let's see where the Lie algebra appeared, which is an important thing. So first of all, what are the two axioms of Lie algebra? So first of all, is the fact that this is well defined uses already the skew symmetry of the algebra. Okay? So for C1, for the map from C2, which is wedge 2 of G, to C1, which is just G, takes A bracket B, and it maps it to the bracket of A with B. Actually, we can try to fix the signs now. So this is A1 and A2. And my differential would send it to minus 1 to the 1 plus 2, which should be minus the bracket. That sounds horrible, so I'm going to add a 1 here, so there's actually the bracket. Okay, so now this is the bracket. Now, why is this well defined? Well, this guy here is minus B wedge A, and this guy gets sent to minus A B bracket with A. So for this to be well defined, I need a skew symmetry. So we've already used skew symmetry in just having this map well defined. Now let's look at what happens from wedge 3. And let's take the typical element is A, B, and C. Well, linear combination of the guys like this. And let's look at the differential. So if I apply my first D, it's going to be A bracket with B, wedge C, minus A bracket with C, wedge B. So I'm just reading this formula. And then the last one is, I need to be careful, it's going to be 2 plus 3 plus 1, that's plus. A wedge, nope, sorry, B wedge bracket C, wedge A. So hopefully that sign is correct. Let's take D of, no, let's check that sign. So that's 2 plus 3 plus 1. That's 6, yeah, good. So here I have a 1 plus 2 plus 1, and here I have a 1 plus 3 plus 1. So that's the minus sign here. Okay, so now let's take D of that. So this is the bracket of A bracket B bracket C minus A bracket C bracket B plus B bracket C bracket A. And well, I probably need to check what the hell I wrote. So let's see. In which order do we want to put this? I'll just shift this guy to the other side of an equal. Right, so put a minus here and write this as A bracket B bracket C. So that's by skew symmetry. These two are equal. And that's with a minus sign. And here I'll keep it as it is. Well, it doesn't matter. A, C, B. And here, this is an A, B, C. And the fact that this is 0 is on the nose, this equation here. This equation here is exactly that equation there. So this is 0. So the Jacobi condition implies that this squares to 0 on C3 to C2. Oh, to C1, I'm sorry. The composition of from C3 to C2 to C1. Just a bunch of applications of the Jacobi identity, just one Jacobi condition plus some symmetry is going to prove the general statement that D squares to 0 on this complex. So D squares to 0, and that's a complex, therefore. And that's a complex that computes the Lie algebra homology of G with coefficients in the trivial representation. So I want to do this more generally for an arbitrary module so that we have one sensible definition. So definition, a Lie algebra module, or a G module, is a vector space M it's a vector space M with a linear map, a bilinear map, which is an action, which I'll write it as A M maps to AM, satisfying the following condition. If you have A and you have B and you have M, you can act this way. And this could be the same thing as A acting M. So that would be more or less like if, well, let me write it. So that's the condition. In other words, the brackets of A and B acts as AB minus BA acting on M. Okay? Notice that I don't have a multiplication in G, so these are all the actions. Okay? So this is like this, and this is like this. This is an element of the module, and I can act by an element of the Lie algebra, and this is an element of the Lie algebra, and I can act on the module. So here A and B are in G, and M is in the module M. So that's the definition of a Lie algebra module. When you have a Lie algebra module, then that complex there can be enhanced. So I'm going to write now CK of G with coefficients in the module M. And this is going to be wedge K of G tensored with M. So now this looks different than this thing here. I need to tensor this sequence that I have there by M. So now this starts with M in degree 0. This is in degree 0. Then I have G tensor M in degree 1. Then I have wedge 2 of G tensor M in degree 2, and so forth. And now I have a non-trivial map that I can choose here, which is the action. So the action is precisely this map that I have there. So as a caveat, notice that K is a module, it's the trivial module over G, where the action is 0. So that's a well-defined module. It satisfies this condition. 0 is equal to 0 on both sides. So K is the trivial module with a 0 action. And then this complex looks exactly like that. Here M is K, and this map is 0. And then tensoring by K, all these tensor products are over the field K. These are all K vector spaces. So all these tensor products are just K is the identity for the tensor product. I probably will talk about this in a second, but tensoring a vector space with the trivial one-dimensional vector space is just the original vector space you started. So this is a generalization of that. In other words, when M is equal to K, that complex is going to be that. So now I need to tell you what the differential is. And now this differential of, well, now I have different objects. I have A1, wedge, AK. And now I have an extra element, which is my element in M. And I tell you what that guy is. And this is going to have that sum that I had before. And now I actually may get wrong the sign, so I reserve that right, and I'll correct it in a second. So this is I less than J less or equal than K. Same thing as before. AI bracket with AJ, wedge A1, wedge AK. Here I and J are missing. So this little hat here means those two are not there in the sum. Oh, So this now is in G and wedge K minus 1 of G. So this I can tensor with M. It's an element in M. And then this other one, there's another sum. I'm going to start with this, and then we'll see if that one is correct or not. So now 1 is less or equal than I, less or equal than K. And what I can do is just leave the guys as they were. A1, wedge AK. And I'm only taking out AI out of here. So I took one guy. So this is now in wedge K minus 1 of G, which is what I want to land. And I need to tensor this with something in M. Well, what I will do is I'll act with AI on it. So now this requires the action. And you see that for the trivial module, this element is 0. That's why I'm left out only with this sum. So I claim that this is a differential. The fact that this squares to 0 is proven in exactly the same way, and you're going to check that you need the Jacobi condition from C2 to C1. But now let's check that this squares to 0 from C1 to C0. From C2 to there, we needed the Jacobi condition from C3 to C1. We started in C3, mapped to C2, and then to C1. Now I'm going to need the Jacobi condition in that case, but we're going to need an extra condition to check that this is a differential from C2 to C0. Okay? So let's grab an element in C2. Let's apply D, and let's apply D. And let's check that that composition is 0. Before, it was trivial because this map was 0. Okay? So now I'm going to grab A, wedge B, tensor M. And I'm going to read this differential. So this differential is, on this sum, we already know. It's just the wedge, the bracket of A with B, tensor M. So that's this sum. It's 1 plus 2 plus 1. It's a plus 1. And here I have two terms. There's a minus when I is equal to 1. And it's going to be B wedge A acting on M. Sorry, there's no wedge. It's a tensor. So this is because I is equal to 1. That's this sign. And then there's a plus when I is equal to 2, which says is A tensor B acting on M. And now let's take D of that. And this is A bracket B acting on M minus B acting on A acting on M plus A acting on B acting on M. Well, actually, I need to check this. Because the way I've defined this thing, the differential is not the action, it's minus the action. Actually, I should have started right there. What's the differential here? It's A tensor M. A is A1, according to my definition. So this goes to minus 1 to the 1. So it would go to A like this. So let's fix that, because I would want to have the action and not minus the action. So let's put here a plus 1. And this is going to change a bunch of things. This is going to change this, and it's going to change this. And now the action is actually this, but it has to be here. On this, well, now it's just that this is plus and this is a minus. And hopefully that's actually 0. Otherwise, we're going to have to change another action here. So this is it, the equation that I have there, that the bracket of A with B on M is equal to A acting on BM, correct? Minus this guy on the other side. So that's this equation equal to 0. So the definition of a module gave me this. Yeah.
Does the motivation for that definition seem a little artificial, like the multiplication there?
Why is it artificial? So the definition of a module?
Yeah.
Well, so perhaps I'm not sure what's a better motivation. So instead of, I'd say no, because we know Lie algebras way before what homological algebra. So I'd say something much easier, which is what's a typical example of a Lie algebra. So if V is a vector space, then you have an associative algebra, which is the endomorphisms of V. With the composition, this is an associative algebra. Right? So the composition of endomorphism of a vector space is associative by definition. And you have the identity, which is the identity of the vector space. However, the same vector space, so this is just as a vector space is the same as that, but the multiplication I'm going to define is different. It's going to be the bracket multiplication, where the bracket is built out of the composition of endomorphisms by declaring that A bracket B is the composition of A with B minus the composition of B with A. This is no longer associative. This doesn't satisfy associativity, but it does satisfy the Jacobi condition. And it's on the nose, skew symmetric. If I change A and B, this guy is minus that. So this is now explicitly a Lie algebra. So same vector space with a different multiplication. And now I can forget that I had a multiplication. I only remember the bracket. So this is the general linear Lie algebra. That's why the GL of V. Okay? So now, whenever I have a vector space, I have this. In particular, if I have M, a vector space, I have GLM. And if I have a Lie algebra over the same vector space K, so this is in bed K, and I have a Lie algebra, this is a K Lie algebra, then I can ask for a homomorphism of Lie algebras here. So what would be an homomorphism of Lie algebras? I defined Lie algebras, and I never defined what is the category of Lie algebras. So an homomorphism of Lie algebras is something that sends an element G to an element here. Let me call it phi of A. And as any algebra, this is a space with a multiplication, and this is a space with a multiplication. So I should send the multiplication to the multiplication. However, I could have taken phi of A, phi of B, and I could have multiplied them on this Lie algebra. I just showed you that any vector space has a canonical Lie algebra structure. So that's a morphism of Lie algebras from G to GLM. Okay? And now I read this by noticing that elements on GLM are actually endomorphisms of M. So suppose that you have an endomorphism, a linear homomorphism of Lie algebras. I'm sorry, a homomorphism of Lie algebras between these two Lie algebras. And now let's pick a vector M in M and A and B in your Lie algebra G. Then I declare A acting on M to be phi of A. Now this is an endomorphism of M, so I can apply it to M. So this is the definition of this side. And now I read this equation. So I'm going to rewrite that equation, phi of AB. So this is an endomorphism of M. And I'm saying that this is phi of A, bracket phi of B. But the bracket was defined as AB minus BA. So this is phi of A, phi of B, minus phi of B, phi of A. And this is an equality in endomorphism in GLM. However, I can apply it to M. I can apply this guy to M. I can apply this guy to M. And this is the definition of a module that I gave there. Conversely, if you have the definition of a module like that, there's an extra condition here that this map was bilinear. This is a linear map from the tensor product to here. So this means the universal property of the tensor product says that if I fix A, this map here is linear on M. So that's the universal property of the tensor product. It's a bilinear map. That means that for every A fixed, the linear endomorphism A tensor dot to A dot dot, well, probably A tensor question mark to A dot question mark, this is a linear endomorphism in GLM, well, in endomorphisms of M. And that guy, I'm going to define it to be phi of A. And that gives me, that equation there on defining homomorphism is this equation. So we get an homomorphism of Lie algebras from G to GLM. So what I've just proven is that representations of G are the same thing as morphisms. So a representation, or I'm sorry, a G module structure on M is the same thing as a linear endomorphism, as a morphism of Lie algebras from G to GLM. Morphism of Lie algebras. Okay, this is general in representation theory, or this applies for any algebraic structure that you know. Whenever you have a set, if S is a set, then the automorphisms of S, bijections of the set to its sets, this is a group. And a group action, an action of G on S, is the same thing as a group morphism from G to out of S. If you want to do this linearly, if V is a vector space, if V is a vector space, a K vector space, then the automorphisms of the linear automorphisms of V, otherwise written as GLV, so those are the endomorphisms that are invertible, this is a group under the composition. And a representation, a G module structure on V, that's a representation of a group G, is a homomorphism of groups from G to GLV. Same thing if you just take, again, a vector space. So now, if you take endomorphisms of V, this is an associative algebra you've already mentioned. So therefore, if you have an associative algebra A, a representation of A on V is just a morphism of associative algebras from A to endomorphisms of V. For Jordan algebras, for all of them, this is the same thing. You just grab a vector space, you construct a natural algebra structure that acts on that vector space, and whatever algebra structure you chose, a morphism of those algebra structures to your preferred one on that vector space is called a representation. So I've given you Lie algebras, groups, and associative algebras. Extend this to Jordan algebras, alternative algebras, whatever kind of algebraic structure you want to work with. These are representations. All right. But I'm interested in homological algebras, and I've given you one example, which is a complex that was built out of a Lie algebra and a module. And the definition, the homology of that complex that was built out of G and M is called the Lie algebra homology of G with coefficients in M. And you can do something very similar for group algebra homology with coefficients in a module V, or for associative algebra homology with coefficients in a module M. And we're going to do those. There are several flavors of each one of them. For groups, there's essentially one. But for associative algebras, you can look at Hochschild homology, cyclic homology. There's a bunch of different kind of homologies that you can try to study. Why is it interesting for Lie algebras? Well, let's look at what are the lower homology spaces. So what is H naught of G with coefficients in M? Right, so probably this homology, I'm going to avoid this letter C. When I write HK of G with M, it means the kth homology of the complex C, the Chevalier-Eilenberg complex that I constructed. So what is this? Well, by definition, this is, we have 0, we have M, and we have G tensor with M. This is in degree 0, this is in degree 1. So the derivative here is 0, the kernel is all of M. And the derivative from here is something non-trivial here. So this guy here is M divided by the action, the space span, the linear span of vectors of the form AM for A in G, M in M. So these are called the co-invariants. I have time, so actually I can say why it's called the co-invariants. I'm going to write this in a different way. I'm going to write this as M divided by G acting on M. And by G acting on M, I mean this, the linear span of vectors of this form. Of elements in G acting on elements in M. So in particular, for example, if M, so let me give you an example of non-trivial homologies. So an example of a G algebra module is M is equal to G itself. And the action of A acting on M, I define it to be the bracket of A with M. So this is called the adjoint representation. And, well, so the fact that this is a module is the Jacobi identity. Right? What I need to check is that the action of A, B acting on M is equal to A, B, M minus B, A, M. And this translates into A bracket B bracket M being equal to A bracket BM minus B bracket A, M. And this is one of the versions of the Jacobi identity that I get. So that's a module. And the zeroth homology of that thing, well, perhaps as a caveat, definition, a Lie algebra G is said to be commutative, or is abelian, if AB is equal to 0 for every AB in G. In other words, the whole G bracket with G is the vector space 0. So H naught measures how far away is G from being commutative. So if you have a commutative algebra, that space is 0, and H naught of G with coefficients in the adjoint module is G bracket G bracket G, modulo G bracket G. So if G is abelian, this is all of G. So if G is commutative, H naught is all of G, is large. There's another, the other end. When is an algebra as far away as being commutative as possible? Well, it's almost like GLV. Well, I think I had little GLV somewhere. The general linear algebra. The general linear algebra has an element that is central. The identity is an element of the general linear algebra. That the identity commutes with anything. But except the identity, the rest is as far away as being commutative as possible. So let me define another Lie algebra inside of the general linear algebra. So now let's suppose that V is finite dimensional, which I never used so far. But when V is finite dimensional, we have a non-trivial representation of dimension 1 of GLV. Again, a representation of a Lie algebra is a morphism of Lie algebras from your given Lie algebra to GL of a vector space. And I'm claiming that there is this GL of a one-dimensional vector space is canonically isomorphic to a one-dimensional vector space because I have the identity here, and this is of dimension 1. So I've given you one representation in this space, which is the zero morphism. So the zero morphism is a good representation for any Lie algebra. But when V is finite dimensional, there's another representation. Well, actually, any linear map works, but there's one that is nice, which is the trace. So you can write this guy as V dual tensor V. Perhaps it's better to write this as V tensor V dual, which is isomorphic to V dual tensor V. And if you have a linear function and a vector, you can evaluate. So this is the evaluation map. So the composition of this isomorphism with the evaluation map is called trace. And the trace is a morphism of Lie algebras. So the trace satisfies something important, which is makes that into a representation. So I'm claiming something here. I am claiming that the trace of A bracket B is for this to be a module, I needed this equation. I needed that phi of the bracket is the bracket of the phi's. So I need that this is the bracket of trace of A, trace of B. And the brackets in endomorphisms in K, this is just trace of A, trace of B, minus trace of B, trace of K of A. But these are just numbers inside of K. GL1 is commutative, so this is 0. So for this to be well defined, I need, and this on the other hand is in GLB. So this is the trace of AB minus BA. And this map was linear. So this is the same thing as the trace of AB minus the trace of BA. So the fact that this is a Lie algebra representation is non-trivial. It requires that the trace is symmetric. Okay? And the trace is symmetric. I'll let you check why the trace is symmetric. Okay, so we have a one-dimensional representation of GLV. And therefore, whenever we have a representation of G on any vector space, we get a new representation of G of dimension 1, which is the composition with the trace. So if you have a representation, you're a Lie algebra acting on a vector space, if you take traces, you get an action on a one-dimensional vector space. That's very similar if you have done for groups. You get characters, and these are characters. Just taking traces, you get characters of representations. All right, so another statement about Lie algebras is that the kernel, so the category of Lie algebra has kernels. So the kernel of a morphism from a Lie algebra to another Lie algebra is a Lie algebra. So that's the set of elements in G such that phi of G of A is equal to 0. That's a Lie algebra. It's more than a Lie algebra, it's an ideal. we don't care about this for a second. I don't want to make this into a Lie algebra course. I just want to motivate examples of homologies. And the fact that the bracket preserves this kernel is trivial because the bracket is computed inside of G. So 0 bracket anything is 0. So, or the bracket of two things that go to 0 is 0. Anyways. So the kernel of a morphism is always a Lie algebra. And the kernel of the trace is called SLV. So these are elements in GLV. But this makes sense only when V is finite dimensional. So these are elements in GLV such that the trace of A is equal to 0. So this is a Lie algebra, and this is a Lie algebra with a bracket. OK, so this Lie algebra is as far away as possible of being commutative, in the sense that if I call this guy G, G bracket with G is equal to the whole of G. So in particular, H0 of G with coefficients in G is just 0. So for an abelian Lie algebra, I get 0. I get the whole Lie algebra as the 0th homology. And for a semi-simple Lie algebra, for a Lie algebra, for a perfect Lie algebra, Lie algebra satisfying these are called perfect. For a Lie algebra like SLV, you get 0 for the 0th homology. You can check that for GL, you're going to get this the same. OK, so H0 measures how far away you are from being commutative on a Lie algebra. How about H1? I don't think I have that much time, so I'll probably talk about H1 and H2 later on. Because I wanted to say something today, which is slightly more important. I wanted to go back to this construction of the homology of the Lie algebra. Okay? I had two things. I had this guy, which was the C dot of G that I started with. Remember, this was just this guy. And then I also had this complex built out of G and built out of M. And this guy was just like this, but tensor with M. So this is the same thing as this, tensor with M, as vector spaces. Okay? And both of these guys came with a differential. And this came with a differential. So I'm going to do this first for cohomology instead of homology because I think it's slightly clear. And then I'll explain what's going on with homology. But what I would want to see is that I want to see this guy as an algebra itself. So this is a complex, and the algebra structure on G made it into a complex. So if I forget about D, and I have just a vector space G, this is always an algebra, where the multiplication is the wedge product. And now, when I made G into a Lie algebra, then I've gained this differential. And this became a complex instead of just a graded vector space. The same thing here. If I forget about this differential here, then this is a module for this algebra. And when I add this differential, then I get the structure that this is actually a module, which is a complex that is compatible with this algebra here. So I'm going to do this for cohomology so that I also introduce Lie algebra cohomology. And that I can hopefully, in the next class, connect this with the RAM cohomology for manifolds. But this is going to give us at least a bunch of examples. So let me construct Lie algebra cohomology now. And this is going to be the dual. So I'm going to define CK. Let's do this immediately now with coefficients in M. And this is going to be, as a vector space, HOMS from ck of g to m. These are linear maps. Okay, so these are linear maps from which k of g to m. Notice that, well, it doesn't matter. So this is going to be a complex, and this is going to be a cohomology complex. So now I'm going to define a differential d that is going to go from ck to ck plus 1. Okay? And it's going to be the dual of the Chevalier-Eilenberg that we just constructed. Actually, why don't we do this on the notes? Why don't we do this more generally? Yeah. So why don't I do this in a more abstract way? Let's do both of them. I think we can stop after I write this. So what is an element here? Let's take phi here. So phi is an element that takes k guys from G, and it gives me an element in M. Okay? So this phi is something that takes A1 wedge AK, and it gives me back phi of A1 AK, which is inside of M. And what I want to construct is d phi that should take one element more. So what I want is to construct d phi, and this guy takes k plus 1 elements. Yeah, I'm sure I'm going to screw up the signs by starting here at 0, but it doesn't matter. I'm going to do this. And I reserve the right to get the signs wrong. But this should be an element in M. And I'm going to just do the same thing that we did before. So we have a sum from 0 less or equal than I less than j less or equal than k. And I'm going to take out ai and aj. And I'm going to put that guy in front of everything else. I'm going to take the bracket and then put a1, ak, I'm sorry. So here I am missing ai and aj. So ai is missing and aj is missing. So here I have, and here's a 0 where I start. So I had k plus 1, I took 2, and I added 1. So this has k guys inside, and phi applies to that, and it gives me an element in M. And I need to put a sign, which I'm going to choose 1 plus I plus j. And then I have the sum over 0 less or equal than I less or equal than k of the other term that we had, which is a minus 1 to the I. And what I can do now is take phi of a1, or a0, I'm sorry, wedge ak. So these are k plus 1 elements. I can take ai out. Now this ai, I took it out. So now there's k elements here. Phi applies, gives me an element in M. And now to that element, I can act with ai. Okay. So that's an element in M. And ai acting on that guy is an element in M. So this is the differential. And this squares to 0. So this makes this guy into a complex. It's now a cochain complex. And the homology of that complex is the Lie algebra cohomology of G with coefficients in M. So this leads to HK of G, well, H dot of G with coefficients in the module M. There's something much more general about this. The fact that this guy is a complex makes hom from this complex into M into a complex. I think I'll do this next class. I didn't need to write this differential. If I have a complex in a category where I can take duals, the dual is a complex. It's just that the differential, instead of going up, goes down. So I'll do that next class. We still have like 10 minutes. So I've defined Lie algebra homology. I've defined Lie algebra cohomology. OK. let's analyze what are the lower groups for these guys. Okay. So what do I have in degree 0? So how does that complex look like, first of all? Right? What is C0? C0 are morphisms from wedge 0, which is just the field K, into M. So that's just M. So C0 is just M. What is C1? And then C negative is 0. C1 are morphisms from G into M. So that's the same thing as G star tensor M. And the morphisms from G to M, it's just that product there. C2 is wedge 2 of G star tensor M. Because wedge 2 of G dual is the same thing as wedge 2 of G star. Here I'm making a statement that is not entirely trivial. I'm saying that maps from wedge 2 of G to M, that's obviously this guy dual tensor M. So this one is easy. Everything here, let's assume things that are finite dimensional. And this is isomorphic to this. So that requires something. Okay? But anyway, so this goes like this. So then I get wedge 3 of G star tensor M, and so forth. Okay, and so what is H naught? H naught now it becomes much easier because I need to define what is this differential, and the kernel of that differential is already the homology because there's nothing in the image here. Okay, so I need to tell you what is this differential here, and I've already written it here. And now we're going to check if one of these signs is wrong or not. Okay, so I have an element here. This is an element phi 0. Phi 0 is something very degenerate that takes 0 elements here, and it gives me back an element in M. So phi 0 is just an element in M. Okay? So that's my guy here. And it goes to dm. And dm is a linear map from G to M, which I read this formula. It takes one element, A, and it gives me back, well, it takes one element. So this sum disappears completely. I cannot take two elements from A. So I'm only left with this. And according to this thing, I am starting with I is equal to 0. So this is minus 1 to the 0, which is good. It's a plus. And I get A acting on phi of nothing. Phi of nothing was my M. So this is just A acting on M. So what is the kernel of this differential? The kernel of these differentials are all those M's such that A acting on M is 0 for every A. So the kernel of this 0 consists of elements M in M such that G of M is equal to 0. So this is known as the invariant subspace of M. These are all the elements in M such that G acts trivially on those. If I have done this for group homology, I would have gotten all the elements in M such that the element of the group acting on M fixes M. It is equal to M. Okay, so cohomology consists, so the H0 of G with coefficients in M are the invariants, not the co-invariants, but the invariants. And this is the dual of the H lower 0. If the category of the field, if the characteristic of the field is 0, well, I have these two functors. If you give me a module, I look at the invariants, or if you give me a module, I mod out, I take a quotient by everything in the image of G. So this is this guy. Remember, is a different beast. Okay. So that's cohomology, and this is homology. I have 5 minutes, so let me say what I wanted to say, which is that first of all, G star is a G module. let me write explicitly what is the action of G on G star. That's called the co-adjoint action. G was a G module, G star is a G module. So A acts on phi. So say phi is in G star and A is in G. So this is now an element in G star. So it takes B in G, and it needs to give me a number. And I'll declare that to be phi of minus A bracket B, which is the same thing as phi of B bracket A. And I claim that this is a representation. So you check that this defines an action of G acting on G star. I'll do this more generally later, but that's it. That this is a well-defined action of A on phi. It gives me a new guy that sends B to this thing. So that's a new linear function on G, and this satisfies the condition of being a representation. Actually, moreover, A acts on wedge K of G star is a G module. Well, I've given you the action on phi, so let's act on phi 1, wedge phi k. And this is just going to be the sum of the action in each one of the factors. So this is going to be the sum of I is equal to 1 up to k of phi 1 wedge. A is going to be acting on phi I, phi k. So now K forms is a G module. And this is an obvious extension of this action here. When you choose K is equal to 1, I am using the action that I'm defining there. So this means that G acts on CK. Let me put a different name for that action. Instead of saying A acting on phi with a dot, I'm going to say the Lie action of A on phi. On phi 1, wedge, phi k. And I'll define it to be this. I'm going to call that the Lie action of A on K forms. OK, so by collecting the sum, so this C dot G, when K is just trivial, this is just the direct sum of all these guys of CK for K bigger or equal than 0 of G star. If G is finite dimensional, then this sum is finite. So if the wedge dimension of G of K becomes 0, well, dimension plus 1 becomes 0. So this is a finite dimensional vector space if G is finite dimensional. So this guy here is a G module. In each summand, I act by that Lie derivative. Acts there, with that very explicit form that I had there. OK. But there's something more. This guy is an algebra. It's a commutative algebra. It's an algebra. It has this product that if you give me a K form, let me say eta, that is in CK of G, and you give me some zeta, which is in C, well, let me put P, and let me put Q of G. So this is a P form and a Q form. Then the wedge product is in CP plus Q of G. And moreover, this is an algebra. It's a unital algebra. Well, no. I need to tell you. Well, let's forget about units for a second. But this is an algebra. And it's a commutative algebra. It's a commutative algebra in the sense that this thing here is not really zeta wedge eta, but is -1 to the p times q times these two. So that makes it into a graded supercommutative algebra. I don't care about the definitions of this thing. I care that I have this product. And this product satisfies this identity. But the important thing is that this Lie derivative is a derivation of this product. With that definition there, this is an immediate consequence of this definition being a sum here. You can check it immediately on generators, that for every element A in G, you have the Lie derivative of A, and that's why I'm calling it a derivative, on eta wedge zeta is equal to Lie A of eta wedge zeta plus eta wedge Lie A of zeta. So what I'm giving you is a map from G to the derivations of this Lie algebra, of this commutative algebra. So this is the Leibniz rule. I have a space with a product, it's this wedge product, and I have a map from G, which is a Lie algebra, to the derivations of these algebras. And the derivations of an algebra are always a Lie algebra. That I'll prove next time because I have no time now. But what we have is a map from G to the derivations of this algebra. So here I'm using the wedge product as a structure, and this is the Lie derivative. So G acts there by derivations. Those derivations preserve the degree. Whenever you give me A and a K form, in each one of these K forms, you get a K form again. And that's a module. So I'll continue next time with extending this. I'm going to construct a derivation of degree -1. That's going to be contractions. And then we're going to prove the Cartan formula. And then I'm going to relate this to things with the same name on differential geometry. And with that, I'm going to go back to homotopies of complexes and the such that we were talking. Oh, by the way, so yeah, so I think I'll put up, someone asked me for it, so